Hello, hello, math magicians. On this beautiful day, we're going to be looking and continuing our journey in the wonderful world of matrices. Today, we're going to be adding and subtracting. So, by way of our goal is to add and subtract matrices using the properties of matrices, which are nice because they're almost the same as stuff we've seen before. So let's look at a warm-up just to refresh ourselves. We'll go ahead and work through this and come back and check your answer. All right, I'm sure you paused, but let's take a gander here. Jedediah, Hafiz's cousin, bought 4.2 pounds of apples and 6 pounds of tangerines for $26.84. The next week, he bought 2.5 pounds of apples and 4 pounds of tangerines for $17.36. Assuming there were no cost changes, how much did he pay per pound for each fruit? We're going to set up the system. We're going to write the equivalent matrix, and then we're just going to jump straight to our calculator and use the ref function. All right, so what does our system look like? First off, we need to define our variables. So, for example, we could say A for apples. I know, crazy talk. Next, we could say something like, I don't know, this one's crazy. Maybe T for tangerines? That could work. So, first off, we do 4.2 pounds of apples plus 6 pounds of tangerines, and all that is going to equal $26.84. Next, we have 2.5 pounds of apples and 4 pounds of tangerines, and all that is going to equal $17.36. So here is my system, and you don't need to write this single bracket here, but oftentimes you're going to see that. Next, what is the matrix? What's the matrix associated with this? So all we need to do is ignore the letters, and we're just going to put in the 4.2, the 6, draw a little line right here, and 26.84. And the next one is 2.5, 4, and 17.36. And there we go. Now all we have to do with this is plug this into our calculator and use the ref function, and it's going to look like this. And if you do set A to be equal to that, then your calculator will show this, and then hit enter. And the answer is, we get the A is going to be $1.78, so $1.78 per pound. And lastly, the 1 tangerine is going to be that, so we're going to round that one up to be $3.23 per pound. And there we go, pretty straightforward. Now our next component that we're going to look at is how do we add and subtract matrices. So let's get something straight first. It is possible to combine matrices as long as they have the same dimensions in order to get new information. The method is simple. We're just going to combine corresponding elements from the matrices. So here's a formal definition from the textbook. To add matrices A and B with the same dimensions, add corresponding elements. Similarly, to subtract A and B, matrices A and B with the same dimensions, subtract corresponding. So this looks really complicated because there's lots of letters and numbers, but the most important part is simply this. If we are doing A plus B, what we do is combine the elements, right? So here, the A11 and the B11 combine here. And next, the A12 and the B12 combine right here. A21, B21, those are corresponding, and they combine like that. And lastly, we have the A22, B22, and those combine right there. So I'm going to show you the middle step, which looks like this, but in future, you could just combine, add this plus this, and write the answer in the next matrix. Okay, And the same thing applies to subtraction. Notice just we are doing subtraction there as well. So given that matrix D, or simply D, is equal to 11, 6, 0, negative 4, 5, and 2, and E is 1, negative 3, 7, negative 2, 2, 4. What are the following? So what is D plus E? So I'm going to write this, but you don't have to do what I'm doing. Okay, the first step here is I'm going to write the matrices when you combine them. But again, it's way more than you need to do. So 11 plus 1. That's it. That's the first component there. 11 plus 1. And then we're just going to keep going here. Here we have a negative 4, negative 2. So negative 4 plus a negative 2. And keep going here. We have a 6 and then plus a negative 3. 6 plus a negative 3, etc. And clearly things are going to, there's a lot to write here, and you don't, like I said, you don't have to. Just jump to the answer. So I'll finish this up though here, and there we go. So now the key is, like I said, is you can just jump to this right here, because what we're doing is just adding things together. So a 12, a negative 6, a 3, a 7, because 5 plus 2, also a 7 here, and lastly a 6. And there's my answer. So D plus E is equal to this matrix. So what is D minus E? So I'm actually going to skip to the answer here, because we can just do this part in our head. D minus E. So D11 minus E11 is simply 10. Continue. 6 minus a negative 3, so that gives me a 9. 0 minus 7, negative 7. Continue. Negative 4 minus a negative 3, so that gives me a negative 2 because it's a plus 2. 5 minus 2, which gives me a 3. And lastly, we have a 2 minus a 4, so that's a negative 2. And that's it. So D minus E is equal to that matrix down below. All right, so one thing we're going to consider, though, is the idea of commutative property. So over here we did D plus E. Now here we do E plus D. And what does happen? So let's, logically speaking, instead of writing the 11 first, we're going to write the 1 first. 1 plus 11. So again, this is a middle step that you don't really need to see at all, but I'm just going to write it so you can see what happens. So 1 plus 11, and then down below here is going to be a negative 2 plus a negative 4, and then continuing a negative 3 plus a 6, our corresponding elements there, and then a 2 plus a 5. Continuing on, we have a 7 plus a 0. And lastly, we have the 4 plus the 2. Now, many of you notice that in adding together, no matter which direction, 11 plus 1, 1 plus 11, we're still going to get the 12. And the same thing goes here. The negative 4 plus a negative 2 is the same as negative 2 plus a negative 4. So because the commutative property works for each one of these individual elements, the commutative property works for the entire system, or excuse me, the entire matrix. So, or matrices, 7, 6, and there we go. So in the end, does the commutative property work? Yes, and this isn't a proof for it, this is just one single example. But since it works for the individual elements, then it works for the entire commutative property of matrices. Now it's your turn. Go ahead and attack, kill, destroy the practice here. Again, you can skip the middle step and just jump straight to the answer. Go ahead and pause, and then come back for the answer. And here are your two answers. When we add them together, negative 12 plus a negative 3 is negative 15, etc. All the way down to the 10 plus 5. And then over here we're subtracting negative 12 minus a negative 3, which is negative 9, and then 10 minus 5, which is a 5. Fill in those ones there. Next, matrix equations. A matrix equation is an equation in which the variable is a matrix. So you can use the very same principles of addition and subtraction, properties of equality, to solve a matrix equation. Let me clarify that. If you add 6 to one side of an equation, then you must also add 6 to the other side. The same applies to matrices. So if you add A to one side of the equation, and A being a matrix, then you're just going to add A to the other side. So that still works no matter what. So let's take a gander here at Ultimate Frisbee and records. The first table shows the Ultimate Frisbee teams with the 4 best records halfway through their season. So here we go. Team 1 has 30 wins and 11 losses, etc. The second table shows the full season, the entire season, for the 4 teams. Which team had the best record during the second half of the season? Okay, so first off, let's set these ones up as matrices. Let me call A the first half, and when I set that up, I get a 30, 11, 29, 12, and clearly I need to make this larger, so erase that, and 25, 16, and 24, 17. Now I can make my bracket. B, we don't know what B is, right? B is the second half. And let me call this one over here F for the full season. And what's this going to look like? Well, same numbers as we see there. And just write them all down. 15, this one's a 58, 24, and this is a 61, 21. Okay. So those are my matrices, and let's see, using the A's, the B, and the F, what my equation looks like. We know that when I add the first half plus the second half, I get the full season. Great. So what do? In order for me to solve, remember I'm trying to get B by itself, the second half, I need to subtract A from both sides. Subtract A from both sides. So now it looks like this. B is equal to F minus A. Oh, great. So all we have to do now in order to get B is to say F minus A. F minus A. Now I'm not going to write all these again inside there because I can do that part in my head. 53 minus, so if we just go by corresponding elements, 53 minus 30, there, we get this. B is equal to, and we get 23. Next, we have a 29 minus 11. 18. All right, continuing on, we have 67 minus 29 to get 38. Boop, boop. And continuing on, 15 minus 12 is a 3. And next, we have 58 minus 25. So that's a 32. 24 minus 16, that's an 8. And 61 minus 24 is 37. And lastly, we do the last element to get 21 minus 17, which is a 4. And there we go. So we know what B is. So now the question is, which team had the best second season, or second half? So the top has the first one, 30-11. But notice this is 23-18. This is a 38-3, a 32-8, and a 37-4. So although Team 4 is down here to begin with, they're actually up higher. And this guy here, we see that team number 2 has the best record, 38-3. 38-3. So there we go. second half of the season, which team? So team 2 has best second half record. And there we go. Now take a moment and solve this equation. The hint I'll give you is use the letters to isolate the variable you're finding first, then just do your adding or subtracting there. Pause and consider. All right, now I'm back. Now, in order to find A, to get A by itself, notice what I have to do. I have to add B to both sides. Add B to both sides. Now, actually, I want to clear this up a little bit and show you what we're actually doing so that we don't confuse it later when we do multiplication. So what I'm actually doing here is I'm going to add B there, and so equals C, and I'm going to add B there as well. So I just want to clarify it that we're kind of in a linear setting here instead of stacking it like this. Negative B plus B, and then plus B over there. Notice it's on the same side. Commutative property works, so I could have said B plus C over here, but later with multiplication you're going to see that things aren't always as we like. So that means A is by itself. We have C plus B. Commutative property B plus C also works, but so now I just need to add B plus C. So A is equal to, and start adding things together. 1 plus 2 is 3. 6 plus 0, negative 1 plus 0. 2 plus a negative 1, 6 plus a negative 3, 1 plus a 6. And then negative 1 plus a 2, negative 2, that should be a 1. Negative 2 plus a 3, also a 1, and 4 plus a 1, negative 1 is a 3. And there you go. And the last thing we're going to do today is use properties of matrix operations, which we already did up there, but I do want to point out a few things here. So what are the following sums? Here we have a matrix A, 1, 2, 5, negative 7, and another matrix here, 0, 0, 0. All zeros. All zeros. So what happens? Well, that one's not overly complicated, right? A 1 plus a 0 is still a 1. And continuing on, a 2 plus a 0 is still a 2, no big deal. And then a 5 plus a 0 is still a 5, no big deal. And lastly, a negative 7 plus a 0 is also a negative 7. So what rule can we think about here? If I have a matrix and I add an empty matrix and there's all zeros, I get the same. I get the same. Now over here, let's look at problem B. 2, 8, negative 3, 0. Negative 2, negative 8, positive 3, and 0. So how are these related? How are these related? If I call this one C, then this one has to be a negative C. It's an inverse, opposite matrix, because everything over here is opposite of everything over here. So what happens? What does that do? So step by step, the 2 plus a negative 2, or 2 minus 2, that gives me a 0. Continuing on, an 8 minus an 8 gives me a 0. A negative 3 plus a 3 gives me a 0. And lastly, a 0 plus a 0 gives me a 0. So what are we seeing here is when we add a matrix with all zeros, we get the same, exact same matrix. And when we add opposite matrix, also known as the additive inverse, we get the identity, the zeros. So your turn. Go ahead and work through these real quick. Pause, and we'll come back and look at properties. Congratulations, you did it. All right, now let's take a gander at the properties of matrices. So, if A, B, and C are M by N matrices, then the following is true, that A plus B is an M by N matrix. That's called the closure property. Two matrices the same size, you'll get out a new matrix that's the same size. So it doesn't change. By the way, I can't add a 2 by 2 matrix like this and then a 2 by 3 matrix, or 3 by 2 matrix. Can't add those together, right? Because there's no corresponding parts down here to go with that. So there's a closure property. Next, commutative property of addition works, that if I add two matrices, A plus B, I get B plus A. Associative property works also. It doesn't matter which pair you combine first, B plus C or A plus B, or you could use the commutative property and associative and say A plus C first and then the B. There's a unique M by N matrix O such that O plus A equals A plus O is equal to A. What's that mean? That's the identity. There's a matrix that doesn't change the identity of A. It doesn't change anything about it. So just like adding 0 doesn't change the identity of a 10. Same thing here. And for each matrix A, there's a unique opposite negative A such that when you add them together, you get 0. Or you get the identity matrix. For equal matrices to be equal, they have to have the same dimensions and same corresponding elements. So these look different, although this is a 2 by 2 and this is a 2 by 2 also. But when you look individually, this one is a 0.25, and that's 1/4. So that's the same. 1.5, 1.5. That's the same. -3, 4/5, 0.8. So these are equivalent. And so if we were setting it up as an equation, we would say they are equal. Okay, so using that to be true here, if we have equivalent matrices, what's true? Well, what values of x and y make these equations true? So we have corresponding elements, so we know that this 9 is equal to this 9. Woohoo, yay! This 10 is equal to this 10. Woohoo, yay! But then we have a 3x plus 1 is equal to 16. And then lastly, we have a 2y minus 1 is equal to a -5. So notice we can now set up equations here. So I can say the 3x plus 1 is equal to 16, and I can also say that 2y minus 1 is equal to -5. So let me just solve these ones individually to find out the values that make this work. So let's start with the x here. Subtract 1 from both sides to get 15. Divide by 3, so x has to be 5. Repeat that process here with the purple. 2y is equal to -4. When I add 1 to both sides, divide by 2 to get a -2. So if I did plug in a -2 right here, I would get 2, excuse me, I forgot my negative down there. There we go. I would get -4 minus 1 is a -5. Ding, ding, ding. And when I put a 5 here, I get 15 plus 1 is 16. Ding, 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 ding. So that indeed works. All right, very last bit here. Go ahead and take a gander at these problems and come back and check your answer, and then we are done. And here we are. Notice that these corresponding create this situation, and these corresponding here create this situation, and both of them yield the same value of x, fortunately for us. If they yielded different values, then there wouldn't be an x that could work. Next, the purple here are corresponding, so we set that up. And just so that you can see what I'm doing here, if you subtract y from both sides here, you just get a single y. And then if I subtract 5 from both sides here, then I get a -6. And when you check that, it does work. This one's a little bit more complicated because we have an equation to manage. So watch this. We have a z minus a 10 equals a 2. It's all corresponding components here. Z minus 10 is equal to a 2. So let's follow that same process here. A 3x minus an x equals an 8. 3x minus x is equal to 8. And lastly, we have, here's my y, my corresponding, so it's 0 minus 2y plus 6 is equal to 4y plus 12. 0 minus parentheses, because that whole thing has to be subtracted, is equal to 4y plus 12. Now solve these individually. And this is what you get. z is 12, x is 2, and y is -3. And that concludes adding and subtracting matrices. Thank you very much, and come back for more excitement later.